Hi guys, guess I'm making a video. All right, today is about angular momentum. I'm not even starting on the handout yet. I need to show you a little bit of derivations. So this isn't really part of the notes, just kind of keep an eye on here. So if you think about momentum in the linear world, we have P equals mv. So the closest analogy to that in the angular world, mass is your moment of inertia and velocity is your omega. So you're going to see that formula. This is for any kind of rigid body, spheres, solids, hollow, all those kind of things. And the I will vary. Omega is radians per second. So when you look at this in general, for just a single point object, so a single mass, think of this as mr squared omega, which is really mr omega. Think about r omega, that is the same as v. So for a point, and I mean a point like if here's a door and here's a hinge and I send a bullet in, that's a small point. It's not a rigid body, but when it strikes here, it's some radius from the pivot. So it's a mass times velocity times a radius. It's not really about the momentum here, it's at impact, that kind of thing. So there's more. If you think about this formula for a second, I'm going to bring this down. We have torque equals I alpha, and that really means, oops, sorry, I'll move it up. This is really omega over time. It's really the change in omega. If I solve for I, I'm going to have torque times time divided by omega equals I. Now, if I substitute that in here, L is going to be torque time over omega times omega. So you see a second derivation for angular momentum. And generally it's listed as the change in the momentum is the torque times the change in time. So I show you these because, dun, da, 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 let's go to the formula page and add the following. So momentum, L equals I omega. If you want to put rigid body there, that's fine. L equals MRV. Okay, we just put it in that order for a point. And then the change in momentum is the torque times the change in time. So yes, your formula page is officially done, and you should know what that means. 10 more seconds, maybe not. You can always play this video over. All right, so I'm gonna take these out and we're gonna go to the actual notes. So let me get my copy and hopefully I won't make up some boo-boos here. So the beginning part here is essentially describing those formulas that I just showed you. All right. In the same way that we did momentum before with linear, when we would say P before equals P after, the same thing for angular momentum occurs. So we're going to use these little examples to kind of show you how this works. All right, so a skater, like a spinning ice skater, pulls their arms in to spin and reduces the radius. What does this do to their velocity? And I mean angular velocity. Probably should put angular on there. So if we think about it, L before equals L after. So I before, omega before equals I after, omega after. Now a person skating, we've got the person here, there's their big skates and their arms are stretched out, and afterwards they're still skating, but the arms are pulled in. Not my best picture. Not looking at this anywhere except as a point. If we substitute mr squared, that's before, omega before, mr squared after, omega after, the mass of the person isn't going to change. So if the radius goes down, that means that the angular velocity increases. Okay, so lower r means greater omega. Why? Because L is conserved. Okay, no outside forces are acting. It was a self inside. All right, let's look at a little more complicated problem. Move this up a little bit more so you can see everything. All right, so a man stands at the center of a turntable. Let's think of it like a merry-go-round. And his arms are stretched out horizontally, and he's got masses, like he's holding on to something. Oh, there's his head, sorry. He is set into motion, some kind of spinning, 5 radians per second. His moment of inertia, just his body, is 6. His arm length, 1 meter. Okay, of course that's not like, he's pretty tall if that's the case. What is his angular speed if he drops his arms? Okay, so here's before, let's look at after. So here's my turntable, put the guy here, and now he brings his arms inside. He still has the masses, and he's going to have some kind of change. All right, so we have I omega, oops, just write that bigger, equals I omega after. So before equals after. But this I is a summation of the guy and the 2 masses. So we have I of the man plus I of the first mass, I know they're identical, plus I of the second mass times omega equals, same thing over here, I of the man, I of the mass, I of the mass times omega after. All right, so we're going to do some substitutions. So the guy, he's 6 plus, well, each of those masses are 5. We're going to do those as points, which means they are mr squareds. So we're going to have 5 times 1 squared plus 5 times 1 squared, all times, I guess I could bracket that, times the original 5 equals. All right, same idea. He's still 6, he didn't change, but this time it's going to be 5 kilograms times 0.2 squared plus 5 times 0.2 squared. I know you could just double those, times omega after. All right, well, 5 plus 5 is 10, plus 6 is 16 times 5. This side equals 80. All right, 0.2 squared times 5 is 0.2, times 2 of them is 0.4, plus 6, this is 6.4 omega after. So when you solve and divide both sides, omega after comes out to be 12.5. And again, it will be, I'll move it up a little bit, radians per second. So you have to pay attention to the moment of inertia. All right, let's go to the back side. All right, number 3. This is the guy that's on a turntable. All right, so again, think of it like a merry-go-round. So there's a guy standing here, and he is on a spinning platform, so it has mass capital M, and we'll have capital R for the radius, and it's 1/2 mr squared. So they're treating it as a disk. Okay, so we'll just kind of label that. Then, that's before. Afterwards, he's no longer there, he's on the edge. Living on the edge. The disk is still M, the radius is still R. His mass I'm going to call little m. But it says he walks to the edge of the disk and his angular speed is reduced to 1/2. So whatever omega I had here, it's omega over 2. I don't have to call it before and after, it's just 1/2. Great. So again, before equals after. So I have 2 things here. I have, for I omega, I have the guy, and he's going to be a point, m r squared. He's little m. Plus you have the disk, but that's a 1/2. Capital M r squared. I'm really bad with these brackets. Omega. The other side, okay, he's little m r squared plus 1/2 capital M r squared. It really doesn't change. Times omega over 2. Well, in this one, his r is 0. He is on the center. He is 0 from the radius, so this is 0. So I end up with 0 plus 1/2 capital M r squared times omega. This case, he is at r, so it's the same. So it's m r squared. It's 1/2 capital M r squared omega over 2. Well, omega is going to cancel. And all I'm left with over here is 1/2 capital M r squared. All right, let's keep going. Oh, hold on, what else cancels? I don't need that r squared, do I? Every term has an r squared. Boom, get out of there. So I'm left with little m times a half, so m over 2, plus, well, a half times a half is a quarter, big M. All right, so I'm going to solve. I'm going to take a quarter of an m off of a half of an m, so I'm left with a quarter of a big M equals 1/2 little m. So if I multiply both sides by 2, right, little m equals 1/2 big M. So there's no specific numbers. The guy's mass is half of the disk, which means he's probably a pretty big guy, because those are big. All right, last one. So this is a bullet, okay? Mass equals 0.01 kilogram. I'm going to convert that as we go. It's fired into the center. So when I really am looking at its momentum, it's this instant that it hits there, because now it's some radius from the pivot. It's not this radius out here, it's when it hits, okay? The center of the door, the mass of the door is 15. This is 15 kilograms, both pictures, okay? So before and after. The door is 1 meter, okay? So this length is 1 meter, which means this distance, if it's halfway, is 0.5 meters. And the velocity of the bullet is 400 meters per second. Find the angular speed of the door. So we work it the same. Sorry, let me move my papers a little bit more. All right, so L before equals L after. But the before is just a point. So this is going to be MRV. Over here, it's going to be I omega. Okay, so M, 0.01, 0.5, 400. That's everything on that side. But this I is now two things combined. There's this point and there's this door. And we know from the lab we have to do this. So this is going to be mr squared plus 1/3 ml squared times omega, because it's got a pivot at the end. All right, so this side, if I calculate it, oh, I haven't actually calculated. Let's see. 0.01 times 0.5 times 400. Oh, it helps if I turn it on, huh? 0.01 times 0.5 times 400 is 2. So the momentum on this side is 2. I'll bring that back in a minute. So mr squared. So we have 0.01 times 0.5 squared plus 1/3, 15, that's the door, 1 squared omega. All right, so 2 equals, you can add all that up if you want. Here, I'll do it here real quick. Well, half of 15 is 7.5. 0.5 squared times 0.01 is this, plus 7.5, sorry. I'm sorry, I did that again. 1/3, I don't know why I keep doing that. That's 5. Equals 5.0025 omega. When you divide both sides, you get omega is 0.399 something, so we'll give it a 0.4 radians per second. All right, that is it. And again, now that you know the formula chart's filled, you know what comes next. Peace.